so welcome everybody. This is talk about Boost.Geometry, and the title says that we're taking on the globe. Well, it's not something, it's not a war, it's just like the direction we're going to. What I'm going to do is that I'm going to give you, my talk is going to be split in two parts basically. I'm going to give you an overview of the library, and then basically what we have been working on for the past 2 years, what are the new features that you should be having in your hand when you're using the library that didn't used to be there 2 years ago. And then I'm going to talk about how we approach the problems that arise when we want to extend our library towards the sphere or the spheroid, basically modeling the Earth in some way or the other. So let me start by, for those of you who are not really familiar with the library, what is Boost.Geometry? It's a geometry that defines concepts, primitives, and algorithms for geometric data structures. And where can it be used? Well, basically, in principle, it can be used wherever geometry is used, but so far the development has been targeted towards GIS applications. So who is really Boost.Geometry? Well, it's an open source project. But aside from the fact that anybody can contribute and everybody is welcome to contribute, you're welcome to contribute anytime you want. There is a core development team which consists of Barend Gerhels from the Netherlands, Bruno Leland from France, Mateusz Loskot from Poland, Adam Wolkiewicz, who is also from Poland and is working with Oracle, and myself, who is located in Greece and also working for Oracle. So if you look at the GitHub repository of the library, you're going to see we have at least, and also the web pages, you're going to see that we have at least a dozen more contributors, either big or smaller contributions. So feel free to go to the website and explore the history and see how it works and all these details. But I'm going to talk a little bit about that now. So the Boost.Geometry library was accepted in Boost in 2009. That was about 4 years before I joined the group. The first release was 147, and right now it consists of about 230,000 lines of source code. I'm mentioning here specifically the C++ 03 in the sense that the library is supposed, and this is on purpose, to work or be compatible with C++ 03 compilers. There is a custom documentation procedure which is based on QuickBook. We have our own wiki page, thanks to Adam, who has created it, and you can go there and learn more about the library. Of course, we're using Bootstrap for following the tickets that we receive, and there is, like any other Boost library, there is a known specific repository for the library. There's also a mailing list for the library that I don't mention in this slide. But we also have, again, thanks to Adam, two very interesting, in my own opinion, wiki pages, which is how you can contribute to the library, which tells you the details about how to set up your GitHub accounts or how to set up your Git repositories and how you can contribute to the library, what is the procedure, what is the workflow, and so on and so forth. And this is also done not only the contribution, but also in the guidelines for developers, where we also say how we approach development in this library. And of course, the GitHub repository of the library is open to pull requests. This should be a request to the develop branch, and this is how the workflow works. I mean, if you want to contribute something or you want to submit a bug fix, this is what you do. You go to your own GitHub page or to your own Git repository, you create a patch fix, you make a pull request to the develop branch of the library, and it gets reviewed, and eventually, if everybody agrees, accepted. So there is one part of the library that not many people know about, but I thought it would be nice to talk about it, and this is sort of an intermediate step between own development and the public repository, whatever is distributed through Boost. There is what we call extensions. It refers to additional or experimental functionality that are available. And this is not really available in official releases. So if you download the official versions of Boost, you will not find anything related to extensions. However, if you get the develop repository, then you will get that for free. And this is part of the develop branch. It's not part of the master branch. And it's tested along with the develop branch at the same level. But this is, as I said, this is really additional experimental functionality, either for our own purposes or for other developers. And there is no real guarantee that this works. It's just, let's say, a sandbox of things that we want eventually to have in the library, but are not really there yet. So I'm now going to switch gears and talk about the library design. So maybe you will hear obvious things, but I think it's really good to hear about obvious things as well. So we have geometry concepts and models, and of course there is concept set checking associated with that. And then the functionality of the library, we can really split it in different categories. There is some core functionality, which is related to types and meta functions. We have also arithmetic operations to geometry, so you can add 2 vectors, or you can add 2 points, or things like that, or subtract 2 points and get a vector out of them. Or scale a vector, for example. There are also algorithms. I'm going to talk about this in details. Strategies, also going to talk about this in some detail. You can think of strategies as the basic building blocks of the geometric operations that we're using to implement these algorithms. And there are also spatial indexes and some utilities. Utilities are input, output, some views, some iterators, some coordinate systems, and definitions of coordinate systems, and some constants. These are really for our own internal view primarily, not all of them actually. I would say that some of the views and I/O are also for the users, but I would say as you go in this direction, it's more like for internal use. But they're there and you can use them. So what is really the design? It exploits namespaces, and there are 3 major namespaces. It's Boost.Geometry, which I will consistently not use in the remainder of my talk. Everything that I'm going to talk about is really inside Boost.Geometry. But aside from this sort of global namespace for the library, there's also the dispatch namespace and the detail namespace. And how do we use those? Well, Boost.Geometry contains everything that is available to the user. This is the front end. This is what you're supposed to use. This is where every functionality that is documented lies in. And then we have the dispatch namespace, which is used to implement the tag dispatching phase or step of our algorithm implementation process. I will show you an example, a very brief and basic example about that, but I thought I would make the distinction between the different namespaces. And then you have the detail namespace, which actually contains the implementation details. And this is where the core or the bulk of the work is really done. So how does this work? Algorithms in our setting in this library are actually free functions, and they take input or the inputs that they take are geometries and possibly some strategies and possibly some other things, but really the bulk of the algorithms are taking just geometries and strategies. So the remaining ones are just a few minor exceptions, and for good reasons. And then for each algorithm, what happens is that we first perform a concept checking step, which says, okay, the geometry that you've given me, is that really the geometry that I should be expecting, or something different? And then the next step is to call some dispatching class, which takes into account the kind of the geometry that you have and basically triggers the corresponding part of the implementation to go on and do the real work, the hard work. And the dispatching is based on tags, and I'm going to talk about the tags in more detail in a bit. So almost our algorithms, and this is something that is intentional, are variant aware. What does it mean? It means that if you plug in a variant of geometries, then the algorithm would still work. It would figure out which is the type of the geometry that you have plugged in into the variant and do the appropriate thing. But be aware that variants are not really geometries for our setting, so they're not considered as a model of a geometry. So this is basically why I say that the algorithms are variant aware and not variant supporting. So what are the kind of tags that we have? We have tags for geometries, we have tags for strategies, we have tags for coordinate systems, and they're all available through meta functions. So as I said, dispatching is done primarily in this namespace, but it happens also in certain cases lower in the hierarchy of the namespaces, so basically in detail. But primarily, this is where things are really happening with respect to dispatching. And then dispatching is done with respect to the geometry type that we have, whether it's a point, it's a line string. This is what you might know as a polyline, whether it's a polygon, whether it's a set of polygons, which we call a multi-polygon. It can happen with respect to the coordinate system, so we have dispatching with respect to Cartesian 2D or Cartesian 3D or Cartesian general, or a spherical equatorial coordinate system or geographic coordinate systems. And there is also dispatching with respect to dimensions. So there might be the case that you want to do different things when you're in 2D and different things when you're in 3D and so on and so forth, or in general dimension. And in some cases, we also do dispatching with respect to the strategies. And this is happening primarily when we're talking about distance computations. I don't really want to get into details about dispatching with respect to strategies, but I just thought it would be good to let you know that this is also happening with respect to strategies, along with everything else that is over there. So I think I mentioned all the information here, but just to make sure that you get the point, the detail is where really the work is happening. So if you really want to look at how we implement our algorithms, this is where you have to look at. But this is not to be used by external users, and there is a good reason for that. Things might change. The API is not fixed. We want to improve our algorithms and make them faster and faster and faster. So this is our own place where we are allowed to modify things without letting you know. So you can look at the detailed namespace, look at how things are happening there, but please do not use it. Unless you want to contribute to it, in which case you want to really look at it and change it and submit your patches. So what are strategies? Our strategies are really, if you want to think of them conceptually, there are small algorithms. There are small pieces of code, or maybe a little bit larger, it depends on what your definition of a small, that says, let me now formulate and solve a specific fundamental geometric problem. And we have different kinds of strategies depending on your point of view. They can be coordinate system agnostic, so they really do not depend on the coordinate system that you're at, or depend on the coordinate system. So we might have a different distance strategy between 2 points on the Cartesian plane, or a different distance strategy with respect to the spherical equatorial coordinate system, and so on and so forth. And can have state or be stateless. So imagine a strategy which is called many, many times. You may want this strategy to really keep some state along with it because of the outcome that it really wants to give you back. So just some examples. A distance between 2 points is a strategy. A distance between a point and a segment is a strategy. A distance between a point and a box is a strategy. Suppose now that you have a segment somewhere, either on the sphere or on the Earth or on the plane, and then another point, and you want to determine whether the point lies on one side of the segment, or the supporting line of the segment, or the supporting circle of the arc on the sphere, and so forth, so on and so forth. This could be a sideness test, and this is one of the strategies that we have. Area is an interesting example of a strategy because it's stateful. So basically, an area strategy says that I want to compute the area of a polygon, and how do I do that? I'm going to split somehow the polygon into triangles. So really the strategy computes areas of triangles, whether these triangles, you can think of them as triangles on the Euclidean plane or triangles on the sphere. But then the sum of the triangles that you have already encountered so far, this is the state that it really keeps up with. So every time a new triangle is looked at, then the area of this triangle is summed up with the current area of the remaining of the triangles that have already been encountered during this process. And this is stateful exactly because you have to keep track of the sum of the areas that you have encountered so far. Another strategy that is very widely used in the library, because it's very fundamental, is intersection points between 2 segments, for example. So what can you plug in there in terms of numbers? You can plug any fundamental number type that you can think of. Well, this is not entirely true. It's really not working when you have unsigned numbers, and the reason is that we tend to have differences when you're doing geometry, and signed numbers are not very good at differences, especially if you expect negative results. But anyways, so in principle, any signed fundamental number type is okay, and we're actually testing our library for that, for floating point numbers and signed integers. But in principle, you can plug in any number that you want, any software-based number type that you want, or any number type that you have implemented yourself one way or the other. There is spatial testing for non-fundamental number types. It's not really done as thoroughly as fundamental number types, but the design is supposed to be there for supporting this kind of number types. So what about rounding errors? And this is a talk by itself, so I'm not going to go into details at all about it. So how you deal with rounding errors is a huge, huge issue. But the way that we're doing it right now is based on heuristics, some heuristics and machine epsilons. And there's also some way of transforming floating point numbers to rationals and then use the rational representation and do exact operations. So what else do we have? We have some iterators that are boost iterator-like. They're helper iterations for our own purposes. Some of them are documented, some of them are not. There are iterators on points and segments of a geometry. And we also have views. One example view is that we want to see an axis-aligned bounding box as a polygon, or we want to see a geometry with a reverted orientation. So instead of going from point 1 to point n, you would go from point n to point 1. You want to see a segment as a line string, and so on and so forth. Unless you really want these views, you wouldn't care about them, but they're there and they're documented. And in terms of I/O, and this is, I think, really important to have, we can export geometries or read geometries in WKT format. This is well-known text format. This is a format used widely in GIS. There is also another format called DSV, which is more basic and appropriate for other cases. And there is also graphical output in SVG format. In terms of utilities, and I guess this is a part of the library where you would use when you would really want to implement something rather than use the library itself, implement something within the library, I mean. There are MPL-like meta functions. There are some boost range extensions that are convenient for our own purposes. There are math-related, there's math-related functionality that is also used heavily, and a few more things that are not so important to talk about at this point. So here's what I wanted to do. I wanted to have a very simple toy problem, nothing to do with geometry, that would give you an idea of how the library is designed like. So here's our model problem. I have a set of fruits. It's apples, oranges, limes, and lemons. And these are the types of fruit that I have. And now I have a few instantiations of fruit. So I have two kinds of apples, Fuji apples and golden delicious apples. I have a lemon model, and I have a lime model, and I have an orange model. And then I want to implement an algorithm that would be able to squeeze these fruits and get the juice out of them. So first thing that you need to do is to define a tag. This fruit tag over there is a tag that tells you, given a specific fruit type, what is its corresponding tag. So we need to introduce some tags. And the specific tags that we're interested in are these tags here that are associated each with a type, not a model, a type of a specific fruit. So what is the next thing? The next thing would be to define our own fruits. This is why I use a model namespace. We also use a model namespace in Boost.Geometry for specific instantiations of geometric types. And here's what we have here. We have specific classes that correspond to our models, or if you want models of our concepts. And then the next thing to do is to be able to register these fruits according to the tags. So we do specialization of the different fruit tag with respect to the different models that I have here for my fruits. And this is how you would do it typically in Boost.Geometry. So here you can see that for a Fuji apple or a golden delicious apple, in both cases, we have this meta function essentially that tells that the type of this specific model is an apple. So, as I said, the bulk of the work is done in detailed namespace. So how you would do the squeezing, this is where you would write it. You would get the detailed namespace, and there you would have an algorithm that says, squeeze me a citrus-like kind of fruit. So this would basically account for oranges, limes, and lemons. And for apples, I want to do it in a different way. It makes sense. They're not the same kind of fruit. So I would have a different algorithm here for squeezing an apple. And what is interesting to notice here is that the type of the fruit is really passed as a plate parameter. And you will see how this is taken into account later on. So this is where I would say the bulk of the dispatching is done. And in this specific example, all the dispatching is done here. What I've done here is that I have a structure that has the same name as the algorithm I want to implement. It's in the dispatch namespace, which means that it's responsible for dispatching. And pay close attention to the fact that this class here is defined or has two template parameters. One is the actual fruit and the other is the tag. And here's where I use the tag to do the dispatching. And how do I do that? I do partial specializations of this class. And for apples, I say, and how do I do for apples, for example? I use I specialize with respect to the tag of the specific fruit, for oranges with respect to the tag of the specific fruit, and for lemons and limes and so on and so forth. And then for each one of those, I basically say, here's how you should implement it. So for an apple, you would use the squeeze apple algorithm. For an orange, a lemon, and a lime, you should use the squeeze citrus-like algorithm. And this is how you would do the actual algorithm. This is just a few lines kind of code. This is in global namespace. And what does it do? Well, I haven't really gotten into detail of how you do it, but in principle, you would do a concept check that the fruit is actually what you expect it to be and not something else, that it's not a cake, it's not a meat, it's not something else. So it should basically be a fruit. It's not milk, for example. And then you would actually call the dispatch class the apply method, the static apply method of the dispatch class with respect to the fruit. And here's what is happening underneath. Underneath, you know the type of the fruit here, and with respect to this type, I'm sorry, you're going to the compiler is going to fill up the corresponding tag here. So from the type of the fruit, you're going to get back the tag, and based on the tag that the compiler is going to fill up for you, it's going to use the corresponding specialization here and actually call the corresponding algorithm. This is basic tag dispatching. I'm not saying that I'm reinventing anything new or inventing anything new. It's just standard tag dispatching, but I thought I would show you how it's done within Boost.Geometry. And this is how it's done. And the interesting thing here is that when you're at the point where you really want to squeeze a specific object of the kind of fruit that you have, you just really need to call squeeze with a corresponding object and you're done. Everything else is taken care of automatically by this dispatching kind of mechanism that I described in the previous slides. So feel free to stop me and ask questions if you want. I am more than happy to answer them. So let's talk about what is the functionality that is available for you in Boost.Geometry. We have points that depend on coordinates. This could be a double or a float or an integer and so on and so forth. The dimension, two-dimensional, three-dimensional, or the coordinate system, whether you're in Cartesian coordinate system or spherical, equatorial, geographic. We have line strings that depend on points. We have polygons that are also can have different orientations or can be defined as closed or not closed. Basically, closeness has to do with whether you require that the first and the last point of the polygon is the same or not. It's a slight optimization in data representation. And then we have multi-geometries, which we can think of them as containers of simpler geometry. So we have multi-points, which is a container of points, a multi-line string, and a multi-polygon. And these are not types, geometry types that have been named in an arbitrary way. These are geometry types that correspond to what is known as the Open Geospatial Consortium standard. So they try to match data types that are referred to in that standard. And we also have some helper data types, which is a segment. So it's basically 2 points, or a box, which is basically something that has a lower end corner and a left bottom corner, a point, and an upper right corner, which is another point. And ring is also you can think of it as a polygon without any holes, basically. It's a closed curve, essentially, consisting of a series of segments. So what else do we have? We have concept shapes for all geometries. We have also macros for adapting existing data structures to geometry. So you can take a pair, for example, and make it into a 2-dimensional point. You can take a tuple and make it with 3 items, and you can take it into a 3-dimensional point. You can take a vector and you can make it into a multi-point, for example, assuming that whatever is plugged in there is a point, and so on and so forth. And we also have macros for adapting your own custom geometries to the concept so that it can work with the libraries. Adapting means essentially providing the proper tags for the geometries and a few more things. So what about meta-functions? We use heavily meta-functions in order to extract type information for the geometries, and such type information will be the coordinate type, the coordinate system. When you're talking about geographical and spherical equatorial coordinate systems, also has to do with the units that you're using, whether it's degrees or radians, the dimension of the geometry. For non-point or even, yes, for non-point geometries, you can get the point type of the specific geometry. For polygons and multi-polygons, you can get back the type of the rings that are used to represent the polygons. And of course, we have, and this is the most heavily used, I would say, tags for geometries, which are used for tag dispatching our algorithms with respect to the type of the geometry. What else? We have a lot of algorithms. And I tried to summarize them in different categories. So we have algorithms for creating and modifying geometries. So here you would see append, which basically says, add one more point to my existing geometry. Make is just a creation thing. Clear says, just throw away everything that I've put in my geometry, all the points in there. Correct tries to modify the geometry so that if you have defined it in the wrong way or not consistent with the concept of the specific geometry, it tries in some cases to make it correct. Unique is able to throw away consecutive duplicate points of your geometry and make it simple in terms of representation and storage. Reverse basically says, go from one, if you have defined your geometry in one way, then go in the other way. So if it's a series of points, then look at the points in the reverse order. And there are a few more also. Then we have algorithms which are related to geometric properties. So for polygons, you want to know about their area. For all kinds of geometries, you want to know their centroid or their length. Well, length is actually really interesting for linear geometries, for geometries that are one-dimensional. And then you can get back the number of points and number of segments of a geometry. If we're talking about polygons or multi-polygons, you want to see the number of holes that you have, which is what we call here the number of interior rings. There is also a perimeter function and so on and so forth. We have set operations. I don't think I should really explain what they do. You probably, not probably, you all know what we're talking about here. And we have relational operations, and there is a slight comment to be made here. These are relational operations that are named and implemented according to the OpenGeo Spatial Consortium standard, and they have to do with how geometries interact with each other. I would say that intersects, equals, and disjoint are very obvious to you, but we also have things like crosses, touches, covered by, and there is also related with them, which I'm going to talk about in more detail in a few slides. Apart from those, we also have some predicate-like algorithms that tell you whether a geometry has no points, whether it's valid and simple. So validity, simplicity is something that is also defined by the standard, and I'm going to slightly talk about it, or we can talk after the talk if you want. And we have a few more algorithms. Envelope basically creates MBRs, minimum bounding rectangles. Convex hull is something that I don't think I need to discuss anymore. I mean, it's pretty obvious. We have distances, we have buffer, which is basically an offsetting algorithm. We have standard, STD standard kind of algorithms, like you can do things for each point or for each segment in a geometry. You can convert one geometry type to another geometry type, or one geometry instance to another geometry instance, actually. And you can do a few transformations as well. I mentioned in the beginning that we also have a spatial index. This is an R3 kind of implementation. We can store right now points, segments, and boxes. Segments is something that has fairly recently been added to the spatial indexing, and this was a huge asset in my own opinion, because it enabled us to simplify some of our own code. We can do incremental or offline creation. We can do dynamic updates, and you can think of it more or less as a container. And it supports also various types of queries, and actually in most of the cases combinations of them. So you can basically say, give me all the geometries in the R3 that contain this point, or give me all the geometries that are disjoint from this point, and so on and so forth. Or you can do combinations of them. So give me all the geometries in the R3, in the spatial index, that are disjoint from this point and intersect this other point, for example. So all these things are really things that you can do with the spatial index. So what I want to start talking about now, and this is sort of the second part of my talk, are new things that you would find in the library after 155. There is a new algorithm which is called crosses. So take a look at the picture over there. you have a segment and a box. The crosses basically tell you whether one geometry really splits the other geometry in two. So I would say that if you look at this picture here, the answer would be false. None of the geometry splits the other one in two. And this is an example piece of code where you would actually call this function, call this free algorithm with this specific input, and get back the answer. So this is how I would write code in Boost.Geometry or using Boost.Geometry. It's implemented for a few geometry combinations, not all of them. We still have some work to do. But for the remaining combinations, you can use a more general functionality, which is called relate. I'm going to talk about it in the next slide. And apart from crosses, we also have added a few more geometry combinations with respect to disjoint and intersects. These are basically the same thing. So before 156, you were able to call disjoint and intersects. These are predicates. These are relational operations for certain combinations of geometries. We have really increased, almost doubled the combinations for which you can call these algorithms here. And again, for the ones that are not there, that are not implemented there, you can still use relate. So what is relate? In order to explain relate, I would have to talk about what is known as D9IM matrix. This is a matrix that, given two geometries, tells you the relative positions of their interiors, and boundaries, and exteriors. It's a 9 by 9 matrix. And this matrix can have entries -1, 0, 1, 2, which are dimensionalities of the intersections of these different aspects of the geometry, the boundary, the interior, the exterior. And, but it can also have a different representation, which is through true and false. And it's basically, or you can think of it in terms of its signature, which is a 9-character string. So what does the relate do? It basically says, let me get this geometry G1, let me get this geometry G2, let me take a mask, which is basically this 9-character string that says what are the relationships between the geometries, and it returns true or false depending on whether the two geometries that I've plugged into the algorithm satisfy the mask that I've plugged in there. Okay? We also have a variation of this algorithm, which is called relation, which is basically takes geometry G1 and G2. So the first one, you can think of it as a verification kind of algorithm. The second one is actually a construction algorithm in some sense. It takes one geometry G1 and another geometry G2, and it gives you back a representation of this D9IM matrix. So how would you use that? Here is my own simple example for doing that. I have two geometries. I have two multipoints here. You can see that these two geometries are disjoint from each other. There is no point in MP1 that belongs in MP2 and the other way around. So I can call relation, get the string out of it, and this is what it would print me. It would say, for example, that the interior of one geometry is disjoint from the interior of the other geometry. It would tell me also that the interior of the first geometry with the boundary of the second geometry are disjoint. And these are the kind of information you get out of this signature here. And then I can plug in the same geometry here, the same geometries here, and the mask, which is associated with the disjoint operation, and it will tell me back, it will verify that this is indeed the case. It will print out true. So if you look at the mask here, there are some asterisks. This means that any output is actually acceptable. So it's like a wildcard. This is the kind of signature that you get in this kind of masks. What about set operations? We have done quite a bit of work in the past 2 years with respect to set operations, and now what we have, which was not in there yet, was not in there in 155, is set operations between point-like geometries, so points or multi-points, and linear geometries, which is either line strings or multi-line strings. So we can get these as input and give you back the set operation output for these geometries. Here's another example. We have two multi-points here, and I'm able to compute now the intersection by calling the intersection algorithm. I compute the union, I can compute the difference, and so on and so forth. So this is something that you can do now for the past 2 years, well, not 2 years, less than that, but right now you can do it. And here's another example. I can get a linear geometry, which is this line string here, and I get a multipoint here. And now I can compute their intersection or their difference. Okay. So what else? We've done a lot of work in distance computations as well. So right now you can take any single piece of geometry combinations and compute their distance, at least in the 2D Cartesian plane, actually in the 2D Cartesian plane. And apart from being able to support every single combination, we have done a lot of work on refactoring the distance algorithm. And how have we done that? There are two basic ingredients that we have injected into our algorithms. It's the use of comparable distances that are used everywhere, and I'm going to talk about it in a minute. And we're also using R trees when we're dealing with multi-geometries, and the reason we're using R trees is for efficiency reasons. So what are comparable distances? Well, you probably all know that the distance between 2 points in the Euclidean plane is given by this formula, but there is a slight catch here that typically in a distance computational algorithm, what we really want to do is not really compute distances, but compare distances. So when comparing distances, there is no reason whatsoever to use the square root over here. So instead of comparing two distances like that, it's really sufficient to compute these quantities here, two quantities of this kind. So there's a gain here. The gain is the square root operation. So if you really want to do things a little bit faster or push your computation efficiency to the edge, you would actually throw away the square root and just do this computation and be done with it. Okay? And this is also true for point segment distances, not only for point-point distances. And what we have done, what has been in Boost.Geometry and has been extended even further in the past couple of years, that we have strategies for computing not only point-point distances and point segment distances, but also point segment comparable distances and point-point comparable distances in the Euclidean plane. So why do we care about that? Well, we care about that because we're really going to use comparable distances in our algorithms internally, and I'll show you what I mean by that. But this is not only true for the Euclidean plane. We've gone a step further, and we do the same thing for the sphere. So this is the formula that you would actually need to use to compute the distance between 2 points on the sphere. The points I'm considering are given by longitude and latitude. So these are angles in radians. And this is the standard formula called the Haversine formula. It's related also to so Hav here is a synonym for Haversine. This is a person that, Haversine is the name of this function, and this is why we have named this strategy like that. And the interesting point to be made here is that if you really want to compare two distances of this kind, you do not really need to compute this expression as it is. You can really do something much simpler, which is basically compute expressions of this kind. So you can throw away an inverse sine operation and a square root. And this immediately gets to a much more efficient implementation. So if you want to compute the distance of 2 points on the sphere, or actually, I'm sorry, compare the distance of two sets of points, 2 pairs of points on the sphere, you would actually be better off, more efficient by using this distance here rather than that distance over there. And in the past year, we've also managed to make this work also for point segment distances. So apart from being able to have comparable distances between points on the sphere, we also have comparable distances between point segment pairs on the sphere. And as you can imagine, when we're talking about spherical distances, the gains are even bigger. I mean, it's not just a square root operation, which is supposed to be very efficient in modern architectures. We're talking about, transcendental functions here, the inverse sine function. So the gains are really, really visible. So I told you earlier that we really want to use comparable distances. Why this is the case? This is an example. This is not exactly what happens in Boost.Geometry. This is not the actual code I mean, but this is essentially what I would write in Boost.Geometry to implement the distance between a point and a linear geometry. Think of the linear geometry as a soup of segments. So how would you compute optimally this kind of distance? You would basically take the distance of the point from each one of the segments of the geometry and take the minimum of that. of those. It's a linear time operation. So there is nothing, algorithmically, there is nothing interesting to be done here. It's a very simple thing. And this is what is happening here. Basically, I have a for loop that says, get me all the geometries of the linear, get me all the segments of the linear geometry through an iterator. And then for each one of the segments, get me the corresponding point, the first point and the second point. And then this strategy that I plug in here is a strategy that tells me, okay, give me the distance of the point P from the segment that has first point Q0, and second segment, the point Q1. This is all that it does. And the remaining part of the loop says, okay, if this is the first time that I'm computing the distance, just store it. If it's not the first time, then if the new distance that I just computed is smaller than the one that I have already computed, just update the minimum result. Okay? It's a standard minimization, minimum find algorithm. Nothing very interesting here. What is interesting, however, is that if you have a strategy, the type of distance that you compute here, it really depends on the strategy. And this is an advantage and disadvantage at the same time. It's an advantage because if the strategy here is a strategy that computes distance in the Euclidean plane, you would get back the Euclidean distance. If it's a strategy that computes distance on the sphere, you get back a spherical distance, which means that the same code here is actually applicable to different kinds of coordinate systems. So I would actually call this algorithm a coordinate system agnostic algorithm. So this is the good thing. The bad thing is that depending on the kind of strategy and how efficient it is, you might do more or less work. So if you're really interested in the distance between a point and a line string on the plane, if you just use the distance strategy, the regular distance strategy here, you would do a lot more square root operations that you would really need, whereas if you were to use a comparable distance strategy here, you would just avoid the square roots everywhere and be much faster. So this would be the standard naive way of implementing this kind of distance algorithm. And here is how we do it. Again, this is sort of pseudocode or a snippet of what is really happening. But this is how you would do it, and this is how it's done in Boost.Geometry. You could take the strategy. You would say, okay, give me back the comparable counterpart of this strategy. Okay. And then you would do all the computations that we did in the previous slide, and then at the end you would say, okay, what kind of distance do you want to get back? Do you want to get back a comparable distance or a regular distance? And there is a conversion here to be done if needed, and that's it. So what I'm trying to say here is that this distance computation here is really done with comparable strategies, so avoiding excessive and unnecessary operations. And then only at the end, we do a conversion if necessary to give you back the result that you want. The other thing that I mentioned that has changed in distance is, and I think this is really important from the efficiency point of view, is how we actually compute them. And I said earlier that we use the R trees. So here's my example case. Let's say that you have a set of points and you have a set of segments modeled as a polyline here. How would you actually compute their distance? And here's how we do it, or before saying how we do it, let's see how we did it. The previous way was really quadratic. You would take each point, compute the distance from the line string, and if the point set would have n points and the line string had m segments, you would basically have an m times n algorithm. So it's really quadratic. It was really quadratic. So this has been changed. The current approach is basically linear arithmetic. Don't take me very formally about the running times. These are practical running times. So if somebody here is an expert in computer science theory, don't shoot me. Okay, this is a practical running time estimate or analysis. So what do? We take an R tree, we put all our points in there, and then after we've created the R tree, we query this tree we query this R tree with the segments of the linear geometry. So for each segment, I'm asking, R tree, please give me back the nearest point with respect to this segment. So this way, for each segment, I have a corresponding closest point. And among all those different point segment pairs, I'm basically computing the minimum, the one that realizes the minimum distance. This is the third step, essentially. Well, the second and the third are done at the same time. The first one is just a preliminary sort of pre-processing stage. Another example. Suppose that they want to compute the distance of a line string and the multi-line string. Well, here is where the new addition of the the modification of the R3 accepting segments gets into the game. This was not possible before 156, but it's now possible. The original implementation before having segments into the R3 was doing something sort of complicated. I had to compute two R3s. I had to do two series of nearest point queries. I had to do call some intersection algorithm. But all this is gone, and we have a faster implementation that does the following. It takes the smallest of the two geometries. By smallest, I mean the one that has the smallest number of segments, gets it into the R3. So there's an R3 created with respect to this set of segments. And then for the remaining set of segments, I'm querying the closest segment in the R3. So again, now I have segment-segment pairs. For these segment-segment pairs, I can compute their distance. And once I have their distance, I can compute the minimum of those distances and get you back the closest segment-segment pair. And once I have the closest segment-segment pair, I know that I can compute the distance and give it back to you. Okay? Pay attention that the algorithms that I just described really do not make any mention to the coordinate system. They are, again, coordinate system agnostic. So I can use, and I'm using the same algorithm for segments or points or geometries on the plane or on the sphere and so on and so forth. So they really do not depend on the coordinate system as algorithms. What really depends is the way you're computing the sort of the segment distances, for example. Yes?
Are you planning to already parallelizing any of these operations?
I think that the medium-term goal is to do parallelizations. At this point, we're more worried, or not worried, we're more targeted towards supporting things in geography. So I would say, yes, this is very interesting, this should be done, but we have something else which is more important for us right now. We want to support geography or computations on the sphere before going into parallelization. The cost here is again linear-arithmetic, and whatever I said earlier about costs holds true here as well. So just to recap what is happening and with respect to distance computations and the strategies that are available right now. So you can compute point-point distances on the sphere. SE means spherical equatorial. You can do point segment and point box. Also, well, this is the symmetric, and you can also do point-point on the Earth, on a geographical coordinate system. This is fairly new. This has been added in 159, I think. Well, segment is not really interesting here, and we have a few more things, two more combinations to worry about that we need to implement in the near future. In terms of what is new here is that the point segment spherical distance strategy did not have a comparable counterpart. Now it has, so it's really synchronized with the rest of the distance computations on the sphere. And here's my first and only mention of my second and only mention of extensions throughout this talk. We had point-point geographic distance strategies in extensions, and these were after massaging and making the code look nice, they're now moved into the library. They're still not fully documented. We expect some changes, but not too much. But the point is that extensions do contain things that are interesting and that are eventually moved into the library when the time is right. I'm going to give you more details about that later, I think. But let me get to another new feature that we have, which is validity and simplicity. The OGC standard has a notion of what geometries are valid and what geometries are not valid. To give you an example, for example, a simple example, if you have a polygon and you have a hole in this polygon that has a common segment with the outer boundary of the polygon, then this is considered invalid. Or if you have a polygon that has a disconnected interior, this is also considered invalid. So what we've done in the past few years in two geometries is that we added functionality for testing whether a geometry is valid and also whether a geometry is simple. Simplicity is also a notion defined by the OGC standard. For example, geometries that have duplicate consecutive points are not considered to be simple. This is a very easy example that I can describe in the context of this talk. And with respect to validity, we now have three different prototypes. There is a standard one that takes a geometry and tells you whether it's valid or not. There is also another one that not only tells you whether the geometry is valid or not, but gives you back a message saying where we have found something problematic. And if strings are not nice, or if you want to globalize your code, meaning that English is not your favorite language but something else, maybe German, then you can use the third prototype, which is returning back some failure code essentially that tells you what has gone wrong. And then you can plug in your own favorite methods to your application. So I now want to switch gears and, yes?
A question about the arteries. When I want to compare the two shapes, to polygons, and I want to know how similar they are, I might use Hausdorff distance or Hausdorff distance up to isometry. And I think arteries would be very helpful in implementing such an algorithm.
Okay.
Is that in Boost.Geometry or?
The only distances that we have right now are Euclidean distances and spherical distances and some geographic distances. So at this point, I'm not sure how easy it is. I mean, you have to define your own distance function, plug it in properly into the library. This should be doable, but not straightforward. It's not there yet. Hausdorff distances are not there yet.
Okay, but I can use the artery as a user, I suppose.
Yes, but you have. I'm not sure how easy it is to plug in a distance function that easily. I mean, it's better to talk with Adam later on, who has implemented the arteries, and he can tell you the details.
Thank you.
My only concern is whether you can plug in your own custom distance function in there, and I'm not sure how easy it is. I think it can be done, but you need to add a lot of infrastructure, basically extend the distance algorithms that we have, or the comparable distance algorithms, so that they understand that you're talking about the Hausdorff distance and not the Euclidean distance. So it will take quite a bit of code to do it automatically.
Okay, thank you.
So one of the things that we're currently working on, and this is really important for us, is to work on the sphere. So we have a few challenges to worry about, and one of these challenges is what do we do, or the things that we're really worried about is what do we do with the representation of points. So 0, 90 and 150, 90 are basically the same point, which is the North Pole. Whatever you see here in terms of coordinates are in degrees, so that it's easier for you to understand what I'm talking about. And then there's also the periodicity of longitude. So this point here and this point here are exactly the same, but the values are different. So we really need to do something about that. And the basic question is, should we normalize coordinates, and when? What are the consequences of these challenges? Well, so the challenges are two different things: poles, which are singular points, and then the other is periodicity of one of the coordinate axes. So these are the two main things that make the sphere different from the 2D Cartesian plane. So what do we need to do? We need to do some special handling for the poles, and also we need to change the semantics of what we call boxes. And boxes, think of them as axis-aligned bounding boxes, or minimum, or related to minimum bounding rectangles. Some of the algorithms in the 2D Cartesian plane may have to be adapted or modified so that they work on the sphere. Some of them are already okay the way they are. And I believe that some normalization is one way or the other necessary at some point in the library. We would like to avoid to do normalization everywhere because this is going to be time inefficient, but some of it might be necessary in certain places in the library. So, as we were thinking about how to extend our functionality to the sphere and to the Earth, we decided a few things, and one of those is that latitudes should be expected from the user to be in that range. We don't really want to have latitudes that are wrapping around, but we want to restrict them in that range here. That's one sort of decision. And the other is that longitudes are expected to be in that range. So this is minus 180 to 540. So this is minus pi to 3 pi. And there's a good reason for that. Hopefully you'll figure it out in the next few slides why it is the case. And then there is another thing, that segments in our library are defined by 2 endpoints. And segment is naturally something which is a geodesic. So when you're talking about 2 points of the sphere, there's a single geodesic connecting them, with the one exception, the points are not dipodal. So if you don't have a dipodal points, then there is one specific segment, and this segment has length which is less than 180 degrees. So internally, the way that we represent segments, we cannot do anything, any segment that is more than 100 degree and more. So this is a limitation which is intrinsic to the way we represent segments. So what about boxes? Well, boxes, as I said, are auxiliary geometries, but they're really important in the sense that this is what the R trees are storing internally, and the R trees and boxes are used heavily within the library for various kinds of computations. They have to be somehow adapted to what it means to have a box on the sphere and the spheroid. So the way that I think about it is that boxes or rectangles, you can think of them in 2 different ways. One way is to think of them as polygons. So it's just a polygon that happens to be axis aligned. That's one way of thinking about them. There is another way of thinking about them. The other way is thinking of them as Cartesian products of intervals. So you have an interval on the x-axis, an interval on the y-axis, or an interval on the longitude axis and an interval on the latitude axis, and your box is nothing but the Cartesian product of those. Well, it turns out that in order to do what we want to do on the sphere, thinking of boxes as polygons is not the most convenient thing to do. It's actually very problematic. And the reason that it's very problematic is that we have cases like this where I cannot really define a box as a polygon. So think of this set of points. These are these 4 points that you see over here. We're talking about the 2 poles and another 2 points here. If you really want to compute a polygon that is coordinate system aligned and contains these 4 points in a minimum way, so the minimum possible polygons, you will have a very hard time figuring out what this polygon is. However, if you think of a box that contains these points, and what is a box now? It's a range of longitudes and a range of latitudes coupled together as a Cartesian product, then this is very easy to do. These points here, they have longitudes that go from 10 degrees to 45 degrees, and their latitudes are from minus 90 to 90. So there is a very natural way of defining a box, a Cartesian product of intervals, basically, for those points here. So this is the decision that we made. Other things that we've done so far on the sphere and in geography is that we're able to check the equality of 2 points, and this needs normalization. What else? We've distance strategies for points and segments. Well, I've talked about distances. The point here is that we still reuse our coordinate system agnostic algorithms. And let me talk a little bit about boxes. How would you compute the boxes? And the problem here is the periodicity of longitudes. So what I'm going to describe here is really related to what is known as the maximum gap problem. You have some points whose projection on the longitude axis is this one here. The axis wraps around, and you want to compute the minimum interval containing all these values. Well, in order to do that, you have to consider basically the maximum distance between the points as well as the complement distance between these points or these longitudes, and you have to take the minimum one. And in this case, this is the interval you're interested in. But there is another case, which is the following. These are the longitudes that I have here. This is the maximum distance between those, and this is the complement. So in this case, the maximum distance between the points, the values here, which is the maximum gap actually, and this is how it's related to the maximum gap, is greater than this distance here. So basically the interval you're looking for is this one, which is, if you look at it this way, it's a union, but if you use periodicity, it's a single interval. And this property here, or this feature here, if you want, is what really triggered us to go for boxes that are from minus 180 to 560. To 540. We really need to transform longitudes by 360 degrees. So another thing that was really interesting is that segments are really different on the sphere compared to the Euclidean point. If you really want to compute the axis-aligned bounding box of a segment, well, in 2D you really need to look at the 2 endpoints, and this is sufficient. And here's the case that you see here. Basically, this is sort of a bounding box for this segment here, but we have this other case here, where in this specific example, the two endpoints lie on the same parallel, but the range of the latitudes of this segment is not really just the range of the latitudes of the two endpoints. So we really need to compute the latitude range for the entire segment. And this is something we've done, and it's already implemented for these segments. And going back to how boxes should be defined, well, this is the actual definition of what boxes should be like. There are constraints with respect to the latitudes and the longitudes. And this is what we expect for the minimum longitude, this is what we expect for the maximum longitude, and they cannot be really far away from each other. Otherwise, we have self-overlapping boxes. Just to mention what we have so far in terms of envelopes, either on the sphere or on the Earth, these are the kinds of combinations or geometries that you can use for computing envelopes. The envelope stands for axis aligned, for minimum bounding rectangles, which are axis aligned. And I would like to switch gears a little bit and talk for a minute or two about my other hat, which is not the Boost.Geometry developer, but the Oracle software engineer. My job is in Oracle is to work with the MySQL optimizer group and support GIS functionality through Boost.Geometry. But you can imagine that when you have a certain product working with an external library, there are issues to be taken care of. And this has to do basically with the release cycle, and not only that, of course, but the major issue I would say has to do with the release cycle and how you port in one direction from Boost.Geometry towards MySQL, whatever it has been done in Boost.Geometry. So we have a different release cycle for MySQL and the general audience releasing with respect to Boost. Boost is now on a quarterly basis. So we have 3 releases per year in MySQL. This is not exactly the same, especially if we're talking about GA releases. We're talking about a 2-year cycle or even more. So what happens is that we have bug fixes that are pushed in MySQL, in the MySQL working source tree, and until a new BG version is formally out. And when a new BG version is formally out, or whether a Boost job, or whether by BG version I mean a new Boost version is out, then we basically take the new version and we plug it into the source code of MySQL and work with that. Okay, and at least this is happening for the development branch of MySQL. Now, what about bug fixes and quality assurance? Where MySQL, fortunately, and I think this has been a very good asset for Boost.Geometry, has a huge and very extensive quality assurance process and a big team. And in the past couple of years, we've had a lot of bug reports from MySQL towards Boost.Geometry, and we've benefited in Boost.Geometry from those because we found a lot of bugs, and we fixed them. And I think this is the good thing to be taken out of it, that if you have a massive amount of testing, then your code gets better. Okay. Of course, you need to solve the bug. You need to figure out how to solve the bugs. But at least it's better to know that there are bugs than not to know that there are bugs. One other thing that is sort of internal to Boost.Geometry, but you may be interested also, may have wondered about it. In Boost.Geometry, we do not yet have geometry collections. This is a specific kind of geometry types defined by the OGC standard. MySQL does have geometry collections, and we had quite a few discussions with my colleagues in Oracle and the optimizer group, the GIS group in there, on how to implement certain things about geometry collections. I think that this knowledge and know-how that we have developed is going to be very beneficial when we end up computing geometry collections in Boost.Geometry. So there are quite a few things to be done in order to feel like we're fairly complete or quite complete in terms of sphere and spheroid support. We need to finish up envelope computations. We need to be able to compute intersection points of 2 spherical segments. And we need to be able to compute the distance between 2 boxes that's on the sphere. And then in geography, there are quite a few more things. We need point segment distances. We need, again, intersection points. More things on distances. And we also need to be able to compute some lengths of segments, which is not obvious yet. areas of geographic triangles, and I'm sure there are quite a few more. But the point is that we have quite a lot of work to do, very interesting work, and I think it's a very challenging part to transform whatever you know how to do in 2D in geography and on the sphere. And with this, I would like to thank you for listening to me, and if there is time, I can answer questions.